Hello everybody. This paper is about spinning light clocks. The title of the paper is Spinning Light Clocks Review Time Contraction in Spinning Non-inertial Frames. My name is Tao. In current physics books on Einstein relativity theory, they mention that time dilation happens in moving frame. However, here we show that time contraction is possible in non-inertial frame. Here is the abstract. Spinning light clocks are invented and their behaviors are investigated. For a spinning light clock, the two mirrors of the clock rotate around a common point, and the two mirrors are abstract at 2 points. The trajectory of the light ray with respect to the mirrors of a light clock is plotted, and it is curved. This means light banding appears. The formula to calculate the time interval for the light ray to travel from one mirror to the other mirror in the spinning light clock is given, and it is found that time contraction happens in the spinning frames. This video shows a stationary light clock. The photon bounces up and down between the two mirrors. Here, the green color disk represents the photon. The blue light segment represents the light trajectory, and the two black rectangles represent the two mirrors. So this kind of pattern can construct a light clock. This video shows a uniform moving light clock. A light clock moves with a constant velocity v towards the right side. Compared to the stationary light clock, the photon has to travel longer in each step, leaving one mirror and reaching the other mirror. So here we can say this kind of pattern can construct a light clock. This slide is about another kind of light clock. It is a spinning light clock, and more specifically, we call it A-type spinning light clock. The two mirrors rotate around a common point, the center. The center is here, and the distance between the center and the two mirrors are same. In video A, it shows the photon light trajectory marked by the blue line and the two mirrors marked by the black color. In video B, it shows the photon and the two mirrors, but it does not show the light trajectory marked by the blue line shown in the video A. In video C, it shows the two mirrors see the curved trajectory of a light ray that leaves one of the measures, the two measures, and reach the other. So here we can see that this kind of pattern constructs a light clock, and we call it A-type spinning light clock. This slide talks about another kind of spinning light clock. It is called B-type spinning light clock. The two men rotate around a common point, the center. The center is here, and the distance between the center and the two measures are not the same, they are different. So we can see here that one measure moves along this circular trajectory, and the other measure moves along another circular trajectory. In video A, it shows the photon light trajectory and measures, and in video B, it shows the photon and measure, but it does not show the light trajectory marked by the blue line in the video A. In video C, it shows that the two measures see the curved light ray trajectory. The light ray leaves one of the two measures and reaches the other measure. So here we can see this kind of pattern can also construct a light clock. We call it a B-type spinning light clock. Uh, Here we put four different light clocks together, and we can see that we can have different ways to construct different kinds of light clocks. Stationary light clock, and uniform moving light clock, and spinning light clocks. Uh, Here we talk about how non-A-type spinning light clock works. If the light clock is at a stationary state, initially the photon is at the position B1, and uh, next step it will go up and hit the top mirror at A1, and then B1, and then A1, and then B1, and so on. So these constructs are stationary light clock. However, if it spins, initially the photon is at the position B1, and the next step it will go to A2, and then to B3, and then to A4, and then to A1, and then to B2, and so on. So these constructs an A-type spinning light clock. Here we talk about how a B-type spinning light clock works. Initially, the photon is at the position B1. If the clock is at the stationary state, next step the photon will go up and hit the top mirror at A1, and then to B1, and then to A1, and then to B1, and so on. This constructs a stationary light clock. However, if the clock spins, initially the photon is at B1, and the next step it will hit the position A2, and then to B3, and then to A4, and then to B5, and then to A6, and so on. And this constructs a spinning light clock, and we call it a B-type spinning light clock. Here we show how time contraction happens in the A-type spinning light clock. Geometrically, we can see here that the distance between B1 and A2 is smaller than the distance between B1 and A1. In the spinning frame, the photon travels from B1 to A2, and in the stationary frame, the photon travels from B1 to A1. This means that the photon travels shorter in the spinning frame, so time contraction happens in the spinning frame. Next step, we do it algebraically. The radius of the circle is denoted as r, so each circle has a radius r, and we have this equation 2r equals c multiplied by delta t1. Delta t1 is the time interval for the light ray to travel from one mirror to the other mirror in the stationary frame, and c is the light speed. In the triangle B1A20, according to the Cosine Law, we have the equation 2, B1A2 squared equals OA2 squared plus OB1 squared minus OA2 squared and multiplied by OB1 multiplied by cosine angle A2OB1. And we can know here that this angle A2OB1 is equal to pi minus angle A2OA1. A2OA1, and A2OA1 is equal to omega multiplied by delta T2, and delta T2 is the time interval for the light ray to travel from one mirror to the other mirror in the spinning frame. And we also have this equation 4 here, B1A2 equals C times delta T2, and OA2 equals OB1 equals R. So B1A2 equals C times delta T2, and OA2 and and OB1, O equals to the radius r, and r is equal to half multiplied by c and multiplied by delta T1. And we plug 3 and 4 into 2, then we have the relationship between the delta T2 and the delta T1. And this relationship is shown in the equation 5. This slide talks about how time contraction happens in the B-type spinning light clock. Similarly, as the A-type, we can see from the geometric aspect that the distance between the point B1 and A2 is smaller than the distance between B1 and A1. B1, A2 is the path for the photon to travel from one mirror to the other mirror in the spinning frame. So in spinning frame, the photon travels shorter, and this results in the time contraction. And now we do it algebraically. In this case, the distance between the center and the two mirrors are not the same, they are different. And we denote the ratio of these two distances at k. K is equal to R1 over R2. R1 is equal to OA1, and R2 is equal to OB1. And we know that R1 plus R2 equal to C times delta T1. Delta T1 is the time interval in the stationary frame. And we know K is not equal to 1 here. If K is equal to 1, it reduces to the A-type spinning light clock, not the B-type here. In the triangle B1A2O, B1A2O is triangle. According to Cosine Law, we have the equation 3. B1A2 squared equal to B1O squared plus A2O squared minus 2 times B1O times A2O times the cosine the angle A2OB1. This angle A2OB1. And we also know that B1A2 is equal to C times delta T2. You can see here the photon traveled from B1 to A2 in the spinning frame. So B1A2 is equal to C times delta T2. And this angle A2OB1 is equal to pi minus A1OA2. And this angle A1OA2 is equal to omega times delta T2. Delta T2 is the time interval in the spinning frame for the photon to travel from one mirror to the other mirror. And we can also calculate the R2 and R1 by combining the equation 1 and 2. And we have the result here. The R2 equal to 1 over K plus 1 times C times delta T1. And R1 equal to K over K plus 1 times C times delta T1. And then we plug the equation 4 to 7 into the equation 3. Then we have the relationship between the delta T2 and delta T1. And this relationship is shown in the equation 8. It has been shown how spinning light clocks work. And what want to be said more that it is possible for clocks to tick more quickly in non-inertial frame, such as spinning frame. And ergodicity may be right. Time may go more quickly or more slowly in moving frames. This slide shows the A-type spinning light clocks with 4 different angular velocities, omega 1, omega 2, omega 3, and omega 4. And omega 1 less than omega 2, and omega 2 less than omega 3, and omega 3 and less than omega 4. In the A type, the two mirrors, one mirror is here and the other mirror is here. The two mirrors move along a same circular trajectory. Okay, we can see. In this slide, it shows the spinning light clock is B type with 4 different angular velocities, omega 1, omega 2, omega 3, and omega 4. And we see here that the two mirrors, one mirror here, the other mirror is here, and the two mirrors move along two different circular trajectories. One mirror moved along this circular trajectory, and the other mirror moved along the other circular trajectory. Okay, that's clear. Thank you.